Is it just me or is it getting hot in here? Because I think it is getting hot, because today we're going to be talking about energetics and thermochemistry. Thermochemistry is just what it sounds like. Thermo, like thermometer, which talks about heat, and chemistry, the chemistry of making heat, or more accurately, the heat made in chemistry. In every reaction, there's going to be some change in energy. Our job to figure out what that change in energy is, predict it, and then harness it for good. For example, in a combustion engine, you're burning a form of a organic substance, some gas, and when you burn that gas, you create energy. If we hadn't figured that one out, well, you wouldn't have a car. But yeah. Okay, so work and heat transfer of energy are very much connected. Work is a element that basically says how much something can do. And energy is a measure of the ability to do work. Work means you're doing something. Something's happening. It's the most basic idea of things happening. The energy comes from the idea of work. When you look at a system where you have a chemical reaction occurring, within that system, if it's a closed system, you're going to have energy possibly leaking out of that system, but mass is going to stay within that system. If you have an open system, that means energy and mass can move in and out of that system. You might ask, well, a closed system shouldn't have the same energy and the same mass? No, because if your energy is not moving, then you can have no reaction, no change in energy, no change in mass. Therefore, there would be no change in anything, no reaction occurring, and nothing but physical changes. However, there can be no change in mass in this case. So energy moving in, mass not moving out. The heat content of a system is considered to be its enthalpy. Enthalpy is simply a complicated word for how much heat something contains, obviously. Heat's a bit of a complicated term. We typically measure in temperature, say, 100 degrees. But temperature doesn't necessarily count for units of heat. Because think about if you had 10 gallons of water at 100 degrees, 10 gallons of water boiling, versus an ounce of water boiling. Well, it would have taken a lot less energy, a lot less heat to be provided to that 1 ounce of water to make it boil than to those 10 gallons of water. That gives you the idea of heat, is that heat is quantifiable, whereas temperature is still quantifiable, but it's applied to a larger mass or a smaller mass. Whereas heat, if you put that same amount of heat into this mass, to something large, to something small, you know how it's going to work. So in chemistry, we like to work with the concept of heat. But a lot of times you end up getting temperature. So what happens if, say, you get the temperature of those 10 gallons of water, and you say, okay, we know how much temperature that has, but how much heat's there? And we're going to talk about how to find that out later on in this video. First, though, we're going to talk about the idea of exothermic and endothermic reactions. All an exothermic reaction is it means that your two or more products are going to react, and they're going to release heat to the surroundings. When you look at the enthalpy of the reactants and of the products, you're going to notice that the enthalpy goes from higher to lower. Higher to lower, I thought you said released heat, right? Yes. It loses heat. In the system, you lose heat. However, the lost heat, because of the law of conservation of mass, and all energy is then conserved, that heat flows out into the surroundings from the system when you lose that heat. Likewise, in endothermic reactions, you have your original enthalpy, and your secondary enthalpy for your products is going to be higher than that. And because that enthalpy is higher, that means this amount of heat has been introduced into that system, and again, you cannot create or destroy energy, at least not in chemistry. So that energy is thus being brought in from the surroundings. It's absorbing heat. If it's absorbing heat, that means it's cold. Keep in mind that there is no constant. In other words, there is no measurement of coldness per se. So when we perceive something as being cold, it simply means that something is taking in or absorbing heat. So endothermic and exothermic reactions are interesting because typically when you think of a chemical reaction, you expect it to be exothermic. You expect energy to be released, which makes sense because chemical reactions typically occur to go from a less stable form into a more stable form. And if you have a more stable form, then usually you're going to end up having more energy available on the side. It requires less energy to keep whatever compound you have together. Because of this, typically in chemical reactions, we'll see exothermic reactions. However, there are certain reactions that you will see they'll be endothermic. And typically to make these reactions occur, to even start, you're going to have to apply some heat to the system, which can be a little confusing. But just remember, if you're adding heat and it's reacting, and then that heat goes away, and it's out cold, well, it's endothermic. It's absorbing that heat. Whereas exothermic, releasing heat. Just because you're adding heat, if you need to add heat to make it react, it probably is actually endothermic. Unless you just have to reach the activation energy. But you can figure that out by measuring your beginning and your ending temperatures and seeing where you end up. Now, when you look at enthalpy changes, you say, okay, we're here, we go to here. We know our beginning and ending temperature. But what's about a more precise way to put it? And those are thermochemical equations. A thermochemical equation is a typical chemistry equation. For example, CH4 gaseous, which is methane, plus 2O2 oxygen will become CO2 gaseous plus 2H2O. It's carbon dioxide plus water. However, at the end of this is added a little sign that says delta H, or change in heat, delta is the symbol for change, equals negative 890 kilojoules per mole. So let's break that down real quick. Negative 890. Negative 890 means that the heat enthalpy is negative at the end of the reaction. It's gone from here and it's gone down. So if our enthalpy is negative, that means that then heat has been released from the reaction. It goes from a high heat, low heat, which means your surroundings gain heat. This means this is an exothermic reaction, which makes sense because it's the combustion of methane. Logically, we would assume that would be exothermic. Then you look at kilojoules per mole. Joules are a measurement of energy. Kilojoules are just a scaled down version of the measurement of energy, joules. Not scaled down, a scaled up version of joules. Moles, you say why per mole? Because the per mole measurement gives you the scaled version, which means if I were to perform this reaction with 2 moles of methane, if I performed with 2 moles of methane, I would instead get twice as much of this, negative 1960 kilojoules of energy. So that gives you your scalable factor. So when you're doing your stoichiometry for combustion or endothermic or any exothermic equation, whenever you have a thermochemical equation, the kilojoules per mole gives you how much you have per each mole for this particular formula. Pretty straightforward. And again, remember when your heat enthalpy is negative, that means it's exothermic. When it's positive, that means it's going to be endothermic. Okay, so then now when we're looking at it, we see temperature. We're going to go back and ask, what is temperature? Temperature is the measurement of the average kinetic energy. So when you're talking about average kinetic energy, you're saying in a particular group of particles, how much energy is typically going to be in one particle. And that's what gives you temperature. And this is why temperature is less effective than kilojoules per mole when you're talking about the amount of heat released by a reaction. Because kilojoules per mole is scalable by the number of moles of reactants you have, whereas temperature is not necessarily scalable. It'll give you what your beginning and final temperatures are. However, if you are applying that heat to a secondary source, for example, if you're trying to warm your hands with hand warmers, it's not going to be able to tell you how warm they're going to be able to make your hands. Okay, so you could, however, as promised, you can calculate your heat changes from temperature changes. And this uses a wonderful formula, which is Q equals MC delta T. MC delta T, Q, Y. Okay, it's pretty straightforward. Q is the heat change, and this is going to be in kilojoules. So how many kilojoules you produce. Then M is what M usually is. That's going to be your mass. So whatever your mass of the products or of the reactants in your chemical reaction is going to be M. Then your specific heat capacity, C, which is a property unique to each thing. For example, for water, you have a specific heat capacity of 4.18, I believe, and every substance will have its own heat capacity. And all it's saying is essentially how much heat it takes to raise that temperature of that substance by 1 degree. Okay? And then the temperature change is the last thing here. So Q equals mc delta T. Delta T is obviously temperature change in degrees Celsius. Or Kelvin. Doesn't really matter because it's a change. So degrees Celsius and Kelvin are the same. Don't use Fahrenheit because we're in chem right now. Okay? So to figure out your heat capacity, which is that wonderful C, you can calculate it by saying heat change over the temperature change. So if you already know something, you already know how much heat is produced, you can then use this to calculate, because if you introduce 100 kilojoules of heat into a, say, 1 liter bucket of water, and then you can measure the temperature change, that would allow you to figure out the heat capacity of water. Woo. Then, now we're talking about this, we also talk about our enthalpy changes. Enthalpy changes, typically, like I said earlier, are going to occur in the direction of lower enthalpy. Things tend to lose energy to become more stable, because if you lose energy, it requires less energy to hold particles together. Whatever requires less energy to hold particles together is going to be the most stable. So you're expecting most of the time reactions to be exothermic, which is part of the reason why it's so easy to burn stuff, but it's so hard to find good chemicals to be used in cooling packs, for example, for medical kits, because there just aren't a ton of reactions that occur that are endothermic. When you're talking about measuring the enthalpy changes of combustion, you can pull it off, but it requires a little bit of special skills, because in combustion, your products are typically both gaseous, especially if you're combusting something like methane, you're going to end up getting water and CO2. When you have both gases, it's hard to measure things like your weight, your mass of your product. So instead what we do is we set up a nifty little system where you have whatever your combustion is, and that heat is then used to heat up a known quantity of water. By doing this, you can figure out, very simply, how much of your substance is combusted. So you can say, we combusted 2 grams of methane, you just mass your burner, you mass your alcohol burner, before and after combustion, get the difference between that so you know how much of your reactant combusted. Then you're going to know how much your water changed in temperature, you know how much water you had, you know what the heat capacity of water is, because the heat capacity of water is always going to be the same thing, bonus, and once you know all of that information, then you can simply figure it out. You plug it into the formula. Your heat of your reaction will equal your heat of water. Tricksy though, because the heat of water is going to be the negative heat capacity of water, because the water is actually going to be absorbing heat from this reaction instead of gaining heat. Okay? Absorbing heat. Because normally what you would have is, when you're looking at this, is your reactants are going to be releasing heat, but that release of heat is then going to be absorbed by the water. So because it moves from one source to another, it flips. Then when you look at it, that's going to in turn equal negative the mass of the H2O. So whatever your mass of your water is going to be negative, times the heat capacity of water, times the change in temperature of the water, and that'll give you your heat of reaction. Once you have your heat of reaction, you're going to simply put that over the moles of methane or whatever you combusted in the reaction, and that'll give you your kilojoules per mole of your reaction. And then you can drop it on the end of a chemical formula and look cool, because you have a delta H equals blank kilojoules per mole. There you go, and it's just that simple. Calculating enthalpies of reaction and solution is similarly simple. All you have to do is, again, you just look at your water, and we're assuming that you'll be in an aqueous solution. You say what your initial temperature is, final temperature, and your masses typically won't change. You do a reaction to completion, so you completely react all your reactants, and at this point, if you know your change in temperature of the water, you know your heat capacity of the water, you can very easily find what the amount of heat produced is. which makes sense when you think about it. So, again, if you're looking heat capacity of water, you know it takes 4.18 kilojoules to raise the temperature of water by 1 degree. So you're saying that if water raises by 3 degrees, well then it's going to be, give or take, 12 kilojoules. And we are almost done. So, the last thing to cover is what happens, actually, that is the last thing to cover. Just a few other tips on calculating enthalpy change in solution. Yeah, done. Yeah, the last thing about calculating enthalpy change in solution is if you have a graphing calculator or some probe to test it with, you want to find when your entire amount of heat has been released. However, then you want to take cooling into effect, because over slower reactions, because most reactions don't occur very instantaneously, they're going to start cooling. So heat's being produced, but as the heat's being produced, it's going to be cooling. So you go and you find the point at which the cooling starts to level out. If you can use a graphing calculator, this is great. And what you end up getting is this downward slope. Then what you do is you extrapolate this slope. So you have a particular point, you say, after 3 minutes of reacting, the temperature was 50 degrees Celsius, then it went down to 49, 48, 47, 46. So take that slope, draw it back up, either on your calculator or usually with just a good piece of graph paper, and then that will give you what your likely maximum heat enthalpy, your enthalpy of reaction was when your reaction began. So draw it up to the point where your reaction began, boom, and you are good to go. And that'll give you that total amount of heat produced throughout the reaction, and it's a bit more accurate of a value. It's going to make your whole labs all go better. And just remember that the big formula from this section is going to be your Wunderbar heat of reaction equals the change in heat it's going to be the change in temperature times C, which is your heat capacity, times your mass of reactants. Okay? Have fun, and see you guys next time. Stay toasty.